Welcome to the EC online seminar series. This time we start with, I would say, something completely new, even for EC. We start with a series called Captivating Cosmology from the Big Bang to Tomorrow. This will be a series of 10 talks. And today we will have Tim Maudlin talking about well, before I will tell his title, I would actually introduce himself first. So Tim Maudlin is professor of philosophy at the New York University and founder and director of the John Bell Institute for the Foundation of Physics. Before he was 25 years, before joining the New York University, he was 25 years at Rutgers University. He has a bachelor in physics and philosophy from Yale and a PhD in history and philosophy of science from Pittsburgh. And his research interests lie preliminary in the foundation of physics, metaphysics, and logic. He's author of several books. I think one of this book will be presented today. And so if you go and you search for his books, then you will find Quantum Non-Locality and Relativity, True and Paradox, Metaphysics Within Physics, Philosophy of Physics and Space and Time, and then the new foundation of physical geometry, the theory of linear structures. And this, it's I think more now his talk today. So I will actually not prolongate too much the introduction. I will just give two more useful information to our participants. That if you have any questions, you have the possibility to ask the question at the end of the talk. There are two ways how to do it. You can raise your hand and you will be unmuted, or you can write the question actually during the whole time of the seminar in the chat. And then at the end, we will read the questions from the chat. And again, people who raise their hand, they will have the opportunity to ask the questions directly. So Tim, I will let you now give your seminar. We are actually at EC, we are all excited already. And I hope everybody else listening to your talk is excited as we are right now. So thank you for accepting our invitations, and we're listening to you. Thank you.
Okay, thank you. Yeah, I should just clarify a bit and hopefully say a little beforehand, because this is going to be, as I understand it, a very different kind of talk than is usually done in this series. And there's a little bit I will say, I'll try to remember at the end about the connection of this to cosmology and the Big Bang, because there is one. But really one way to think about this is that in order to make progress in physics, including cosmology, we have to find a way to put together quantum theory and the theory of relativity. And that has turned out to be just a very difficult thing to do in any kind of rigorous way. And I'm going to be making some suggestions about why that is and maybe a way forward. And I should also mention this work actually is not in the volume that was mentioned. It's the second volume, which does not yet exist. It's not out, I mean, because I haven't finished writing it, of New Foundations of Physical Geometry that this work will be the end of. So let me just share my slides. Okay. And I should also say, although this may be on a topic that most people here are not that used to thinking about, because this is a brand new idea, as far as I know, and developed essentially from zero, everybody should be able to follow what I'm doing. There's no technical background or whatever that you would really need. I'll try to explain the main issues at the beginning, but then there'll be a little bit of geometry that everybody should be able to follow. Okay, so why is there a problem putting together quantum theory, which is more or less the theory of matter that we have, and relativity, which is our best theory of space-time structure? Why is there such a difficulty joining them together in some way so that there's a single theory that covers both, which of course there must be because nature has both. One of the issues is non-locality, that quantum theory displays a kind of breakdown of classical locality in a way that was demonstrated by John Bell. I think that Bell's discovery here is, in some sense, the most important discovery in the history of physics. He proved, for those of you who are not that familiar, Bell proved a set of inequalities, just purely mathematical inequalities, that if you do experiments in labs that are very far apart, or technically at space-like separation, so light from one lab couldn't get to the other lab in time to have any effect on its experiment. What Bell showed is that if the world is local in a certain sense, if causation and so on can't itself go faster than light, then there are certain mathematical constraints on the kinds of correlations you could see between the outcomes of experiments done in these labs. And so he proves this theorem, and then it's just a matter of going into the lab. Well, first you notice that quantum theory seems to predict violations of this inequality, and then you go into the lab and check, and indeed there are violations of this inequality. So there is some kind of non-locality in nature, and that means that in some sense there are connections between events that have to be superluminal. And the question is how to implement that cleanly in the physics, right? How to actually write down a physics in an explicit way that will have this consequence. Now, I'm going to talk about how this is done in a particular understanding of quantum theory, not because I want to convince you this is the right way to think about quantum theory, but I'm just making a conceptual point. So I want to talk about what's called sometimes called Bohmian mechanics, or the pilot wave theory, the de Broglie-Bohm theory, which is a way of understanding quantum mechanics in the sort of way that John Bell insisted we need, which is where it's all in some equations, right? The physics is reduced to some clear, explicit, precise equations that you can solve and analyze, and not some hand-wavy, vague talk that you don't quite know what to make of. For example, if someone says, well, things go a certain way in the physical world until there's a measurement, and then they go a very different way, and then you wonder, well, what constitutes making a measurement? I mean, what is the physical content of that? So this is the kind of thing Bell didn't like. And this pilot wave theory is the kind of thing he did like, just because it's an explicit theory. So let me explain that theory for those of you who don't know it. The ontology of the theory, that is what the theory actually postulates to exist physically, consists of two parts. There's a quantum state, which is what you would be used to if you've studied any quantum mechanics, so a thing that's sometimes called the wave function of a system, which is the main thing quantum mechanics uses to represent physical systems. But in this particular theory, there's something in addition to the quantum state, which is a bit unusual, which is that it postulates there actually are particles. That when we talk about particles like electrons or the Higgs particle or whatever, we're talking about that because there really are particles. There are point particles that are moving around and that follow continuous trajectories. So in this theory, there are such particles, and they do in fact move in a certain way. How do they move? Well, once I tell you what there is in the world, then I need to give a dynamics. That is, I need to give some equations that specify how those things behave. And because we have two pieces of this theory, the quantum state and the particles, I need two pieces of dynamics. Now, for the wave function, for the quantum state, the dynamics is the usual one that's used in quantum theory, which is given by the Schrödinger equation. This equation always obtains in this theory. So there's no such thing that you might have heard of, the collapse of the wave function. That doesn't happen in this theory. So it's always the wave function, the change in the wave function is governed by this equation. Again, without going into much detail, you notice on the left you have you have this psi of x and t, that's the wave function. And this equation is telling you how it changes in time because you've got deep psi dt, and that's equal to this Hamiltonian operator h hat operating on psi. So you can fill in particular h hats and you get a dynamics that tells you how the wave function changes through time. It's a deterministic equation, it's a linear equation, it has various mathematical features that are well understood. But in this theory, in addition to the wave function, in addition to the quantum state, we have these particles. And the point of the theory is to say that everyday things like tables and chairs and stars and planets are made up of these particles. And so you want to know, well, how do the particles move? And so I need a dynamics for that. And that's given by a second equation, which is called the guidance equation. And there it is. Again, you don't have to worry too much about exactly what's going on, but you'll just notice that, again, on the left, dq k dt is how the kth particle's position changes in time. So it's just telling you how the particle moves. And on the right, which specifies how it moves, is an equation that just involves psi. It involves the wave function in a fairly simple, it's really quite a simple equation. And this is why it's called the pilot wave theory. Basically, the point of having the wave function, the point of having the quantum state is that it guides the particles. It tells them where to go. And it does so in a way that's specified by this equation. Good. So to understand quantum theory in terms of this picture, you can always go into any actual experimental situation because you have these two explicit equations and say, all right, what's going on, right? What actually happened according to the theory, or what could have happened according to the theory? And we want to particularly look at the moment at spin experiments, which are probably fairly familiar if you've studied any quantum theory. You can, quantum particles, electrons and neutrons and so on, protons, have a feature we call the spin. And the spin is like an intrinsic magnetic moment. It's as if they're little magnets with north and south poles. And when you take an object like that and put it through an inhomogeneous magnetic field, a magnetic field that changes its strength as you move around in space, that can deflect the particle. And so experiments that look at these effects of spin, obviously are called spin experiments. They tend to, at least originally were done with things called Stern-Gerlach magnets. I'll show you a picture of that in a second. And these magnets can be oriented in whatever direction you like to make the magnetic field vary in that direction. So we can orient the magnets in the in a direction we can call the x direction, and then prepare a beam so that all the particles, when they're fed in, are deflected in a particular direction when fed into that beam. Let's say we'll call it the up direction. So I feed this entire stream in of particles and they all get deflected up. And then I can turn the magnets 90 degrees into the z direction and apply them to that same prepared beam. And then what quantum theory predicts and what actually happens is now the beam splits. Half the particles go one way and half the particles go the other way. In other words, if I can predict with certainty what will happen if I check for spin in the x direction, then I become maximally uncertain what will happen if I check for spin in the z direction. That's an instance of what's commonly called the uncertainty relations. The better I can predict one thing, the worse I can predict something else. Now, what we have here is a deterministic theory. So the exact physical situation at the beginning of an experiment, together with the laws, determine how the experiment will come out. So we can go and ask, well, what if I do this experiment where half the particles are deflected up and half are deflected down? What makes the difference, right? What is different about an up deflected one from a down deflected one? And in this theory, there must be an answer. Now, the answer can't be in the quantum state because the quantum state is the same in all these cases. So the only other place you could find a difference is in the initial positions of the particles. And so the outcome of the experiment must depend on those initial conditions. And in fact, they do according to theory and in an extremely simple way. So just so you can understand this, and it's about the easiest thing you can imagine. So we have here a Stern-Gerlach magnet. You'll notice it's got a pointy part on the top and a non-pointy part on the bottom. You could say that the top part would be the north pole of a magnet and the bottom the south pole. And because of the different geometry, the magnetic field is now not uniform. And you'll notice that the rule is very simple. All of these indicated flow lines tell you what a particle would do if it started at one of these various different positions on the left. And if the particle starts above the midline, above the dotted line, it'll be deflected upward a certain amount. And if it starts out below that midline, it'll be deflected downward a certain amount, and nothing goes straight through. So you get these two clumps of the particles that end up here and the particles that end up here. And that's just a matter of where they started out. So you couldn't ask for a more simple and straightforward explanation of the observed statistics than that. And there's nothing particularly mysterious or puzzling about that. According to the way this theory is set out, when I prepare a beam, I can prepare the quantum state, but I can't prepare the precise positions. There'll always be a kind of statistical spread in the initial conditions. And so there'll be, some of them will be above and some of them will be below. Now, there's a second kind of experiment that now starts to illustrate the issue of non-locality, the issue that Bell talked about. And as I said, non-locality has to do with effects of an experiment done in one lab on an experiment done in another lab very, very far away, arbitrarily far away, according to the theory. And so in order to illustrate this, I need more than one particle. I need a particle that's going to be sent to Alice in her lab and another particle that's going to be sent to Bob in his lab far away. And it turns out that these pairs of particles can be in special states, entangled states. The one that's usually looked at for a pair of particles, like a pair of electrons or a pair of neutrons, is what's called the singlet state. And again, quantum mechanics makes very specific predictions about the outcomes. Sorry, the dog is whining. About the outcomes of experiments done on these pairs of particles, even when Alice and Bob are arbitrarily far apart. So let's just talk about that. In the singlet state, what are these predictions? Well, it's that if Bob and Alice, the only one I'm going to talk about now, they're more interesting ones, but if Bob and Alice set their two Stern-Gerlach magnets in exactly the same direction, if they both check in the x direction, or they both check in the z direction, then the predictions of quantum mechanics are very simple. It's that 100% of the time, Alice and Bob will get opposite results. If Alice gets up, Bob will get down. As for whether it's Alice getting up and Bob getting down, or Alice getting down and Bob getting up, the theory doesn't make a strict prediction. It says half the time it'll be like this and half the time it'll be like that, but all the time they'll be exactly opposite. They'll be anti-correlated. All right, this is an example of a kind of correlation that was first noticed by Einstein and was made the centerpiece of a famous theory that Einstein wrote with Podolsky and Rosen called the EPR paper in 1935. Now, you might think, well, there's nothing very puzzling about that, right? Why should I be puzzled that whenever Alice sees one thing, Bob sees the other? As people say, if I take a dollar bill and rip it in half and send the two sides off, one to Alice and one to Bob, then always they'll get up different sides, right? One will get one side of the bill and the other will get the other side of the bill. And there's nothing particularly spooky or non-local about that. So these phenomena, this particular phenomenon of this perfect anti-correlation could be explained in a purely local way, where there's nothing spooky, no spooky action at a distance, as Einstein would have said, going on. But it turns out that what Bell showed, and I'm not going to go into that proof here, is that although you can have a local explanation of that particular experiment, if Alice and Bob, instead of measuring in the same direction, start to measure in slightly different directions, if they adjust their magnets so that there's some angle between them, then the quantum mechanical predictions cannot be explained in a local way. These perfect correlations could be, but as a matter of fact, in this pilot wave theory I've been talking about, they're not. In the pilot wave theory, it is the case that you have a kind of physical non-locality here. And I just want to go through this. If you're interested, it's nicely explained by David Albert in his book, Quantum Mechanics and Experience. So what's the situation? I have a pair of particles. I'm sending one off to Alice this way. I'm sending one off to Bob that way. The quantum state of that system is a singlet state, so I know what that is. In this theory, I also have the precise positions of the two particles. And you might think, well, it must be that always one particle starts out above the midline and the other particle starts out below the midline, and that's why this one goes up and that one goes down. But that's not correct. In this theory, they can both start out above the midline, or they can both start out below the midline. And then you might say, well, but then what determines which goes up and which goes down? And the answer, it's a very simple answer in the non-relativistic theory, is that the particle that gets to its detector first does what you expect. If it's above the midline, it goes up. If it's below the midline, it goes down. And the particle that gets to its detector second then is automatically required, or it follows from the equations of motion, that it'll do the opposite thing. Okay, so if in fact you did this experiment according to this theory, if you did this experiment and both the particles start above the midline, if Alice measures hers first or puts hers through her apparatus first, she'll get an up outcome and Bob will get a down outcome. But if Bob puts it through his apparatus first, he'll get the up outcome and she'll get the down outcome. So this is this non-locality. That is, in order to understand what happens in Alice's lab, you have to take account of what happens in Bob's lab. If Bob decides to be lazy and not do his experiment at all, then Alice will get one result, but if he decides to be very ambitious and do his early, Alice could get a different result. So you just can't predict what she's going to see without taking into account what he does, even though he is arbitrarily far away, so far away that what he does cannot be communicated to Alice at signals that go the speed of light. All right. So the main thing is which of these two experiments happens first. Good. Now, that's the way the non-relativistic theory works. But you say, gee, that's non-relativistic. I want to transition. I want to somehow write this theory or adjust this theory to work with relativity. I want to transition to a relativistic theory. And the problem is that in relativity, in the standard way of understanding relativity, there is no time order between these two events if they're that far apart, if they're at what we call space-like separation. There's no fact of the matter at all. There's no physical fact which happened first. There's no time order. There's no, as we say, global time order that orders all the events in the universe, so that for any pair of events, you can ask whether A is before B or B is before A, or they happen at exactly the same time. That's a part of the structure that gets lost in relativity. It doesn't exist. It's technically, if you have a Lorentzian metric, in a relativistic setting, there is not what we call a global foliation, a kind of global time structure that orders events in terms of earlier and later. Gone. So now you say, but wait a minute, in the non-relativistic theory, I really needed this time order, right? It was important physically whether Alice or Bob does their experiment first. And now I want to somehow produce such a theory in a relativistic setting. I no longer have this global foliation. What am I going to do? And one answer, one that I have always thought was kind of reasonable, is say, well, if I really need it physically, I'll just put the foliation back in, right? I will add it, even though it's not part of classical, special, or general relativity. I'll put it back in, and I'll be, in order to use it to implement this non-locality that Bell discovered. Now, I've been arguing for decades that this is a reasonable thing to do. Most physicists don't like it. The reason they don't like it isn't that they argue it can't work, but that it's this kind of comment that Russell made about certain philosophical theories, where he says, well, this theory seems to have all the advantages of theft over honest toil. It just seems too cheap or too easy to say, well, I could use a foliation. I don't have one. I'll just add one. Now, I personally have always been a little puzzled by this, because it seems to me that to say that something's cheap is, as far as its cost goes, a good thing, right? It's better if things are cheap than expensive, assuming they work perfectly well. What would happen in the case I just gave you is you can start with a relativistic space-time that has a light cone structure and all the normal structure of relativity, and then add to it a foliation, and now you have a new structure. You're not going back to classical physics, you're going forward to yet a new structure. People don't like it. Okay, I'm not even going to argue about that here. I've gone through all this to explain why one would want, just in order to be able to implement quantum theory, you would like a foliation. It would be a nice thing to have. Now, the rest of this talk is going to be this new stuff which you've never seen before. So, suppose we don't do what I just suggested, that is, start with a relativistic space-time and add a foliation to it. But suppose we start with an entirely different structure, completely different, absolutely non-relativistic looking structure, and see whether the relativistic structure can naturally emerge from it. That is, even though at a fundamental level, the space-time structure does not look at all relativistic, maybe in a very simple and comprehensible way, something that does look relativistic can emerge from it. That's going to be the scheme now. And I'm going to show you that this actually can happen. And it can happen where the underlying or the exact or precise structure is as non-relativistic and non-classical in every respect as you can imagine. That even in that situation, in a very natural way, something that at macroscopic scale kind of looks classical and looks relativistic can emerge, and can emerge in an extremely natural way. So that's what the rest of the talk is going to be about. Now, the place to begin here is, let's imagine that space-time is discrete. And this is already making a change from all classical physics. Because in classical physics, you start with space, say, being thought of as a Euclidean space, which is a continuum. And if you do general relativity, the first thing you pull off the shelf mathematically to describe space-time is a four-dimensional differentiable manifold, which is a continuum. But we've known from antiquity, people have thought from antiquity, maybe space and time are not continuum. Maybe they're discrete. Maybe they have a kind of atomic structure when you get all the way down to the finest possible scales. And we all understand how something that is discrete at a fine scale can nonetheless look continuous, like if you have good resolution on your laptop, it might look like there are nice continuous lines on your screen, but in fact, all there are pixels, right? Discrete pixels that are either on or off. So the general idea that we can't tell by any casual examination whether space and time at a fundamental level are discrete and continuous. That's been recognized for well, since antiquity. But I don't think the discrete possibility has been explored enough. Certainly not since Newton, not since Galileo, not since essentially the beginnings of modern mathematical physics. Continua were always taken to be the structure of space and the structure of time. So I've been looking at this and thinking about how you might implement the idea of a discrete space-time. Now, the first thing to say is there are any number of ways to do it. And if anybody says there's some physical consequence of just having a discrete space-time, that can't be right, because there are just too many ways to do it. You can't just saying it's going to be discrete doesn't tell you enough. I've been thinking about how to do this in a novel way that I call full discrete geometry. So I'm going to tell you about that very quickly, and starting with the purely spatial structure. So now forget about time. Time's going to play a very important role in a minute. But for the moment, just forget about time and just think about space. What could a discrete space look like? Well, the thing I'm calling full discrete geometry is called full because it has atomic elements of all dimensionalities up to the dimensionality of the space. So if I have a three-dimensional space, I'm going to have zero-dimensional atomic elements, one-dimensional atomic elements, two-dimensional, and three-dimensional atomic elements, which, for obvious reasons, I'll call 0, 1, 2, and 3 elements. By saying they're atomic, I mean they don't have any parts of that kind. So the zero elements are zero-dimensional atomic things, zero-dimensional things that have no parts. So you can think of those as points. That's fine. That's what we always thought points were. One elements will be one-dimensional atomic things, atomic lines, if you will, but you can't think of them the way you do in Euclidean geometry. In Euclidean geometry, lines are made of points. In fact, every line, no matter how short, is made of an infinite number of points, because in Euclidean geometry, you can always bisect any line and then bisect that and then bisect that and then bisect that forever. So these atomic one-dimensional elements are not composed of points. They don't contain points. They are bounded by points. Each one is bounded by a pair of points. So the fundamental relation between different dimensionalities of these elements is that some bound others, right? N elements bound n plus 1 elements, if there are any. So every one element has exactly 2 zero elements as boundaries. And once you specify what bounds what, you can then make decisions about what is adjacent to what. So in a discrete space, unlike in a continuum, if I pick out a point, I can ask what are the nearest points to it, the ones next over, the adjacent ones. In a continuum, there's never an adjacent point. There's always, no matter how close I come, there's closer ones. And in a discrete space, there are adjacent ones. But once I have this relation between the zero elements and the one elements, I can say what is adjacent to what. So if I have a zero element and a one element and another zero element that is its other boundary at the other end, then I would say those 2 points are adjacent. And if I have 2 one-dimensional lines and they share a boundary, if they are both bounded by the same point, then I'll say they're adjacent. Good. So all of that is going to be well defined. So here are some examples of one-dimensional discrete spaces. They're made up of zero elements points and one elements these lines. The middle one is what would normally come to mind if I said, give me an infinite one-dimensional discrete space. Okay, it's dot line, dot line, dot line forever. But from what I've said, the other ones are perfectly good one-dimensional discrete spaces as well. In the upper image, you'll notice there's a point that bounds not 2, but 3 different lines. In the lower image, you'll notice that there's a loop, but you should not think that that loop itself is the boundary of a pentagon or anything, because there are no two-dimensional elements at all. They're only one-dimensional and zero-dimensional elements. So these are some discrete spaces, discrete one-dimensional spaces. They're not all that interesting. Things get interesting when we go up to 2 dimensions. When we go up to 2 dimensions, we now have to make a decision. Namely, what do our 2 elements look like? What do our atomic surfaces look like? What kind of geometry do they have? And here you have a choice point, and you have any number of choices you could make. And so, as I said, again, if someone asks, what are the physical consequences of making space and time discrete? The answer is, you have to tell me a lot more before I can answer that. Now, physicists have looked at this. The most common, and as far as I know, almost the only choice that's ever made is what's called, to use a simplex as your 2-dimensional element. And a simplex, as the name suggests, is the simplest 2-dimensional polygon, namely the triangle. And then if you go up to 3 dimensions, the simplex is the simplest polyhedron, namely the tetrahedron, which is, of course, made of triangle. I mean, its bounding faces are all triangles. And so lots of physicists who have looked at the idea of a discrete, somehow discretizing space or discretizing space and time, immediately go and do it in terms of what are called simplicial complexes, sets of these simplexes, which means you're dealing with points, lines, triangles, tetrahedra, and so on. That's not what I'm going to do. So this is the first thing to notice. And it's not obvious what to do. And when I was writing the chapter on this, I rewrote it 4 different times. First with triangles, then with square, as we'll see, with quadrilaterals, and then back to triangles, then back to quadrilaterals, back and forth, until I figured out what actually made sense. In any case, what I ended up doing, and the thing that works for my purposes, is when I go up to 2 dimensions, not to use triangles, but to follow Euclid. So what did Euclid say? Euclid said a point is a dimensionless thing, right? It has no dimensions. If I take a point and move it, again, now through a continuum, it draws a line. So that gives me a 1-dimensional thing. And now if I take the line and move it, the whole of it, in another direction, if I have another direction to move in, that will trace out a quadrilateral or a square. I mean, you might say a square, right? I take my line and now I move it, and now I take that square, if I have a 3rd dimension and I move it, it traces out a cube, or properly a heptahedron. So this is what we're going to do. We're gonna take as our 2-dimensional elements, not triangles, but quadrilaterals. I'll call them squares because it's easier, but they're not officially squares because I haven't defined angles or lengths or anything that you'd need to really define a square. And the 3-dimensional elements will be, we'll call them cubes. Again, they're just things like cubes and square-based solids of that sort that have 6 quadrilaterals as sides. Okay, so sorry, again, this is where I'm just saying you like 1 dimension, 0 dimensions, 1 dimension, 2 dimensions, and then pull that up 3 dimensions. Good. So let's just look at the 2-dimensional case, pure geometry, pure spatial geometry. And so this picture, the square grid, is the space. The elements of the space are a finite number of points, which you can think of as the vertices here, or where the lines intersect. A finite number of 1-dimensional elements, which are easy to see, and a finite number of 2-dimensional elements. And the 1-dimensional elements bound the 2-dimensional elements, the 0-dimensional elements bound the 1-dimensional elements, and so on. Now, that space has a kind of intrinsic geometry to it. Even though I haven't defined length, even though I haven't defined angle, there's a natural way to talk about the geometry, because when you do discrete things, there's always what's available counting measure. You can always count things to get a kind of sense of, as it were, how big they are. And the geometry you get in this case is what's called taxicab geometry. It's kind of familiar because it's what would happen if you got into a cab in a city with a square grid of streets and you tried to figure out how much you're going to have to pay to get from point A to point B. It doesn't really matter, as it were, how far point A is from point B, but it's how far the cab is going to have to drive, and it's got to be constrained to stay on the streets. So in this picture, you'll see point C, and then these other points that are indicated with the dashed lines between them, they would be what would correspond to a circle in this geometry. That is, those are the points that are 3 units away. That is, the least number of moves you have to make on this grid to get from C to any of those points is 3. So you can go, 3 out straight to the right, 3 out, 3 up, or you can go 2 up and 1 over, or 1 over and 2 up, and you get this thing that is what corresponds to a circle. And of course, it's not a circle. It doesn't look like a circle. And it not only doesn't look like a circle, these things don't behave like circles. They don't behave in a very fundamental way like circles. So if I look at point D in that diagram, and again start growing circles out from it, which will be these growing diamonds, you'll notice that when they meet, when the circle of 3 units from D will meet the circle of 3 units from C along that entire edge, along an edge that contains 4 different points. And that can't happen in Euclidean geometry. In Euclidean geometry, if I have 2 circles, they either don't intersect at all, or they intersect at 1 point, or they intersect at 2 points, and that's it. They can't intersect at 3 points because 3 points determine a circle. So even without talking about lengths and distances, just topologically, these things that correspond to circles in this taxicab geometry don't behave like circles. So this is very non-Euclidean. It's of course also very non-Euclidean because you don't have an infinite number of directions from any given point. You only have 4 directions you can go in from any given point. Good, so that's the discrete spatial geometry. Now we're going to add time. And we're going to add it in a discrete way. So again, just as for any spatial point, you can talk about the next ones or the nearby adjacent ones. Now, for any event, you can talk about the next ones or the most adjacent ones in time, the ones that happen next from that one. And so because time, unlike space, has a direction from earlier to later, we're going to use directed elements, arrows, rather than undirected elements. So we're doing directed graph theory now, as it were. How am I going to add the time structure in? Well, again, I have an infinite number of choices. Even in the simplest case, which is 1 plus 1-dimensional space-time, so 1 dimension of space and 1 dimension of time, as always, there are infinitely many ways to do this. Let's just look at some of them. So I have here 2 copies of a 1-dimensional space, the blue lines, right, with dots and lines, and then another copy above it. And then I'm going to indicate with the arrows immediate successors in time. And in this diagram, what I've decided is that each 0 element will have only 1 successor in time, and each 1 element will have only 1 successor in time, which are given by these vertical arrows. So that's one way to add time in. But that's a really bad way to add time in, because what I would like to do is to say things like this, that particles have to travel along continuous trajectories through space-time. And by a continuous trajectory, I now mean always to an adjacent point, always following the arrows. But if there's only 1 arrow from every point, then everything's going to be frozen. If I have 2 particles that are right next to each other, they'll always be right next to each other if they're in this structure. So I can do that. It's sort of what you might think of, if you're familiar with this, as a kind of discrete version of Newtonian absolute space and time. It doesn't do me any good. It's not useful. All right. Well, having only 1 successor isn't good. I can go to the other direction, extreme, and have an infinite number of successors. I could say, well, let me draw an arrow from every single point in one layer to every single point in the next layer. So as it were, every point in the next layer is an immediate successor. And you would get something that sort of looks like this. You see it gets very, very messy. And now there's nothing like a restriction on relative velocities. That is, if I have two particles that are right next to each other at one time, at the next time step, they could be as far apart from each other as you like. They could have separated any amount. This is the kind of discrete version of what we call neo-Newtonian or Galilean space-time, if you're familiar with that terminology. That's also not what we want. Because one thing we know that relativity has in it are light cones. It has a light cone structure that somehow restricts how particles can move. And this wouldn't have any restrictions. So I don't like that either. Well, one doesn't work and infinitely many doesn't work. I have a whole, lot of things in between. But it turns out that what works really nicely, as we'll see, is the next simplest thing, which is just for each event in this 1 + 1 dimensional space-time to have exactly two successors, right? So you can, as it were, either move to the right or move to the left, up one and then move to the right or move to the left. And then from point A here, you get something that looks kind of like a light cone. If from point A, you always have to follow the arrows, you'll always stay within a certain wedge that goes out diagonally. And you'll notice there's only one path. We can now talk about connectivity, path connectivity, by which I mean how many continuous paths connect a pair of points. So from A, there's only one way to get to D. I got to go through B. But from A, there are two different ways I can get to E. I can go A, B, E, or A, C, E. So this, again, is just because this is discrete, I can just count and look at the number of paths. So this is going to turn out to be an absolutely essential quantity in this theory. In this discrete theory, you have a counting measure. You can count the number of continuous paths that connect any two points or any two n elements. And that's going to give you a finite number. Could be 0, could be 1, could be any number, any finite number above that. Now, how do I count these paths? Well, let's just look at the 1 + 1 dimensional case. It's familiar. Everybody knows this from Pascal's triangle. Pascal's triangle is just essentially counting continuous paths from the apex down to any point in the middle. So if I start at the top of this triangle and I go down to one of the, well, at the bottom, one of the ones marked 15, there are 15 different ways to get from the top down there. You're essentially just counting paths. Now, there's a lot I could say about 1 + 1 dimensional space-time, but I want to go to 2 + 1 dimensions. I don't have much time left. I'm getting really to the point. In 2 + 1 dimensions, what do? Well, the two-dimensional space is our taxicab space, and I'm going to do the same thing. I'm going to take the space, I'm going to take a copy of it and kind of shift it so that the middle of one square is above a dot below it. And then from each point below, I'll draw exactly 4 arrows out to the corners of that square. So I get this kind of truss system. Here's how it looks from above. The cross-hatched ones are below, the solid dots are above, and you'll notice from every cross-hatched one, you have 4 arrows going out in 4 different, as it were, in 4 different directions. Good. And then I can just build that up into a huge discrete space-time structure. Now I want to talk about path connectivity in this structure. How do I count the paths between things? Instead of using Pascal's triangle, you use this thing called Pascal's square base pyramid. It's a nice thing. I was unaware of it until I started doing this. But just imagine I have a bunch of cubes and I'm stacking them up on top of each other as here. So each cube rests on 4 below it, and that rests on 4 below it. And again, I just want to count the number of paths from the apex down to any cube. I just add the numbers that are above and work down that way. It's a little hard to see in 3 dimensions, but if I go down 5 levels in this pyramid and cut through it, this is what I would see, level 5. Of course, along the four corners, there's only one path that goes down. I've always got to go down that edge. But the other things you notice about this is it has two interesting features. One is that along each edge, you have just Pascal's triangle. Those are the numbers from Pascal's triangle, which if you think about it a minute, has to be, because in order to stay along the edge, you always have to move in one of the ways you can move. You always have to keep moving in that direction, so that takes it out. And then the other interesting thing is you notice this is a multiplication table, right? That is, the numbers in the interior you just get by multiplying the numbers along the edges that intersect. So the 24, you'll notice, is at the intersection. If you go up to the top, say you get a 4, and go to the side, you get a 6. So it's just a multiplication table with the usual Pascal triangle numbers along the edges. Now, suppose this gets really big, as you would expect. If space is discrete, the level of discreteness is very, very fine. Everyday things are many, 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 many levels up. And we need to make a calculation about this. And we're going to use Stirling's approximation, which is a good approximation to the numbers proper numbers you get out of Pascal's triangle. As those numbers get large, you get closer and closer to a Gaussian distribution, which I've given you here. And the main thing about it, I want to calculate path connectivity. I know how to do it. I use Stirling's approximation for these numbers, which goes to a Gaussian, which I've given you. And if I ignore the normalization constants, it's just e to the minus x squared. So along each edge, the numbers distribute like e to the minus x squared, where x is the distance from the center of that out toward the side. And therefore, for 2 + 1 dimensions, I have e to the connectivity at any given level will be some constant, e to the minus x squared times e to the minus y squared. And that's e to the minus x squared plus y squared. Now, what you have to notice about that is that it tells you that on a given level of this, the connectivity to good approximation goes as x squared plus y squared. So any 2 points where x squared plus y squared are the same number, the path connectivity will be essentially the same. But x squared plus y squared is the formula for a Euclidean circle. So at the level of path connectivity, strictly Euclidean structure is emerging from this underlying structure that's as non-Euclidean as you could imagine. The underlying structure has preferred directions. The underlying structure, again, the things that kind of correspond to circles are really quadrilaterals. But at the level, once I put time in and I look at path connectivity in time, what emerges strictly is Euclidean structure with no preferred directionality. And it gets better. That's what happens if I look at path connectivity and I cut through my space horizontally. If I cut vertically in a 1 + 1 dimensional space-time, in Minkowski space, the main structure, the structure of proper time, the structure that defines relativity, is going to be a hyperbola, which is given by the quantity delta t squared minus delta x squared equals constant. And if we look at path connectivity in that way, I haven't been able to derive it as cleanly, but I've done it numerically. Here's the exact formula. If I go up to level n, and I'm counting x from the center point and x and y from the center points, this is the exact formula. And I can actually plug that in and get numbers. So if I go up 800 levels and I look at the very center and calculate the path connectivity, I get this number, 3.5 times 10 to the 478, right? That's big numbers because of the combinatorics. But just remember that, 3 point something times 10 to the 478. So that's a dead center 800 levels up. Now, suppose I go 10 more levels up to layer 810, and I want where I have to move out from the center to get down to that connectivity, because the connectivity is going up along the center. How far out do I have to move along the x-axis? Well, you just fool around with it and you find the best approximation you can get is this one where I go out 75 units, and there I now have 3.1 times 10 to the 478. So the path connectivity from 800 to 810 75 0, 800 00 to 810 75 0 is essentially the same. What if I go out along the diagonal? So instead of going out along X, I go equally along X and Y. The nearest point is at 53 out, and that gives me 3.3 times 10 to the 478. So the points 0, 75 and 53, 53 have about the same path connectivity. And you'll notice that the square of 75 is almost exactly the sum of the squares of 53 and 53. Again, the Euclidean circle is emerging. But now I can ask another question, and I'm really almost done. In relativity, what I expect are these hyperbolae to show up. And if I go up from 810 now up to 1,000, I go up to level 1,000, and I calculate where a relativistic hyperbola in a continuum would hit that level, I can get a number, right? It's a precise number, 354.6. I round to 355. So in this discrete structure, I'm going to make a guess that the path connectivity, if I go up to level 1,000, should be about the same if I go out 355 units over. And when I actually plug it in, here's the number I get. 3.3 times 10 to the 478. So there's no doubt that relativistic structure is emerging with no twiddling of knobs, with no setting of any free constants, almost precisely. The structure of relativity emerges at the level of path connectivity from this discrete underlying structure that has a preferred foliation. And so if that's what space and time were really like, and if the physics were sensitive to path connectivity, the physics would, as it were, appear to be in a Minkowskian space-time, even though the underlying space-time is as far as possible as you can imagine from being that way. Now, that's the end of this story. I will make one more comment. Another nice thing about discrete geometries like this is you don't get singularities. All you ever do are add finite numbers of finite quantities. Things can't blow up. So in terms of cosmology, the Big Bang can't be the beginning. What we would naturally say is that the problems that arise in general relativity of the emergence of singularities can't happen here. The problems that arise in quantum field theory of the emergence of singularities can't happen here. And so you would expect that the space-time structure should continue back, and you should be able to figure out what was going on back before the Big Bang, if this is what's going on at the fundamental level. So, sorry, I thought I had an hour. Maybe I didn't realize that. I did finish within an hour, and that's the end of the talk.
So thank you so much for your talk. I was thinking I will see at the end again the picture of your seminar. Well, I missed it because when we announced your seminar, you sent us a picture.
Yeah, I thought you were going to use that picture.
Oh, sorry. Yeah, we use it. Yeah, but I was thinking it will be in your presentation. That you can
well, now I hope you see why that picture struck me as being so relevant, because that geometrical figure is sort of there.
I see. So we have 3 raised hands. Let's take Massimo Materassi. Please, Massimo.
Yes, very quick, because I am in a library that is closing right now. So my question is, how far are you from general relativity? So how far are you from curving these checkered structures?
Right. That's a
Thank you.
That's a really good question. What happens here is the thing that you think of as the light cone, which is an absolute limit that's constraining the particles. It really looks like a square-based pyramid, like an Egyptian pyramid. And in order to get around the light cone, you have to go inside it a bit. But if you go inside it, then that gives you the possibility of a physics where you can bend these things to some extent. You can bend these conical structures a little bit and stay within that square-based pyramid. So I haven't worked out the details, but you can sort of see how the basic idea of explaining gravitational effects by curvature could be implemented here. You won't get all of the possible general relativistic models, right? You won't get things with closed time-like curves. There would be a limit. You would essentially have a built-in limit to how much curvature you could have. But you can sort of see how that would go once you make the sensitivity to path connectivity clear.
We have a next question is from Luciano Burderi. Please. Yeah.
Yeah.
Unmuted. Now you are unmuted.
Can you hear me?
Yes.
Yes.
Okay. Well, the question is, in all this construction, you have made interesting speculation about the way in which points connect each other. But what is the role of the mass? This is completely independent on this parameter, that is mass, that in principle has an important role in the dynamics of particles. Can you comment on that?
Sure. So the idea is that mass typically appears, and this, I mean, the one place this wouldn't be true is in general relativity, but mass typically appears in the dynamical equations for the material objects, for the fields or particles or whatever. What I'm giving you is a kind of spatiotemporal background in terms of which those dynamical equations would be written. And so the mass would appear in the normal way in the dynamical equations, and the dynamical equations themselves would be specified with respect to this kind of fundamental discrete structure.
Thank you.
One more question from Richard Frazin.
Yes, hear me?
Yes.
Okay. You'll have to forgive me. Almost all of my research is on classical optics for things in astronomy, so I'm not used to thinking about this stuff. But I didn't see the connection between the non-locality and the discrete space-time structures.
Right.
So how does the discrete space-time explain non-locality?
Right. So explain would be a little strong. What I said was that the easy way to implement non-locality is to have a global foliation that you can make reference to. And that's what you lose in relativity. But
well, foliation, what does foliation mean? Foliation means assigning a time to every, like, so well, what's foliation?
Right, so it just means that the space-time structure naturally resolves into a series of stacked sheets, right? Now you could assign numbers to those sheets and call them a global time. It doesn't really matter. It's what's important is just that you've resolved the space-time into these stacked sheets so that you can make precedence judgments about what happens before what. And in this discrete space-time, that sheet structure is there. It's there from the beginning. You don't add it. It's a natural part. Pretty much, it's very hard to do a discrete structure that doesn't have a preferred foliation to it. So I didn't explain exactly how you would plug that foliation. I mean, if you're doing the kind of Bohmian thing that I talked about at the beginning, it's easy to see how you'd write down the guidance equation using that foliation to specify the dynamics.
So what you're saying is that the non-locality pops out?
Well, the non-locality would be a consequence of the dynamics you write down. I'm not saying that it's not that any dynamics here will be non-local, but it's that if you have a non-local dynamics, and we seem to need it, the easiest way to specify one is by reference to a global foliation. And here I'm giving you the global foliation to use for that purpose.
So we have 3 more raised hands. Now I would like to go on to Keith Horn. Yeah, now you are unmuted.
Thanks. You are relying on triangles for your spatial units, or sorry, squares, quadrilaterals. Is that fundamental in the theory? I mean, you said you liked it, but can you do it with triangles? Can you do it with hexagons, etc.?
Right. I mean, that's a great question. There are very specific reasons why I was forced to use quadrilaterals even before I got to the time part. I mean, I made this decision when I was just doing the spatial stuff. I can say that with high confidence, if I'd been using triangles all along and you run these numbers, they wouldn't come out anything like what I just gave you. That is, you would not get the emergence of anything that looks relativistic. You know, hexagons, I've basically only looked at one thing in detail, which is the one thing I did. If it turned, it would be interesting, of course, to find out that this is a generic phenomenon, that many discrete structures would give you this emergence. But my guess from my understanding of why I'm getting it is that actually you'll only get it if you use quadrilaterals and then cubes.
So we have one more question now from Norma Sanchez. Yes, yeah, you are unmuted.
Good afternoon from Paris. Thank you.
Bonjour.
As I see from your presentation, path connectivity and triangulation in some sense give to you the key ingredients for the output you want. The question is, why this input? Because one can define perhaps other, I mean, from the mathematical point of view, other connectivities, other foliations, and
Right.
then you will not obtain that. In my mind, I finish that and so. In my mind, the question of non-relativistic or relativistic is not the key point, but the question is about the foliation or the discretization. And discretization of a space-time is an idea which has been also implemented from quantum theory. And I think that the key here, the underline, is a quantum theory, because even what you explain give me the remember of the path integral formulation of quantum theory. Because if you don't take the physical path, say, connecting one event in another, you don't reproduce quantum theory in the canonical wave and so on. So I think that this is interesting from the point of view of the discretization of a space-time, perhaps from this idea of the foliation, but it could have I mean, there is a great path to do, to go to dynamics and to some physical. Another point, and I finish, is about the physical parameters, the physical or even mathematical parameters you need to introduce here, because there are some parameters. The foliation or the discretization intrinsically introduce a parameter, a distance and so on, because we know also to go from quantum from classical to quantum, you need a parameter or a fundamental or a constant, and the same thing is to going from non-relativistic to relativistic. So what if you obtain here relativistic from non-relativistic, but that is not magic. Is because there is in the path connectivity and foliation, you have intrinsically a parameter, which is here unit, but is there if you want to interpret in the physical terms. Thank you.
Yeah, so let me completely agree with one thing. As a purely mathematical fact, right? So there's the purely mathematical fact that if I calculate path connectivity in this structure, I get emergent structures that are very nearly isomorphic to relativistic structures. Now, does that make any difference to physics? Well, only if the physics cares about path connectivity, right? And classical physics wouldn't, right? Classical physics, it would just be, you know, an interesting observation maybe, but of no physical significance. But of course, as you say, you turn to quantum theory and you have the path integral formulation, which typically in a continuum isn't even well defined, right? Because I mean, most of the paths are fractals. But quite independently of this, you say, gee, actually, the path integral formulation suggests that path connectivity does play a central role in quantum theory, yes. and might be the kind of thing that the physics cares about, right? Responds to. Now, just to notice that is not to implement it, but that's right. Now, it's true that there have been other ways that people have tried to discretize things. I mean, one thing is the so-called causal set approach, which is also discretization, but they're not doing this and they don't end up with anything that looks at all like this. So just discretization alone won't give that to you. And the last thing is you said, well, there's a parameter. I guess I really disagree. I don't think I've put any parameters in. I'm just using counting measure. Using counting measure doesn't mean that I'm assigning distances or anything. I have a discrete structure and I'm able to count it without adding anything to it. And yes, what I get by counting in a certain way turns out to be provably isomorphic, right? Or emergently, approximately isomorphic to structures that I get in relativity.
Yes, but I agree. I mean, but in the distance or in the way you have the Gaussian and I mean intrinsically you are using unit. You are using parameters equal to 1. You don't need here, but you have when you said discretization. Well, there is a limit in which the discrete space-time become continuous, and there is a length, perhaps a minimal length from which you can you don't have any more resolution. So a parameter is intrinsically in the way you are you have a foliation because you have some distance. And what is this distance? If you are talking about Minkowski space in some sense. Well, if you talk about Minkowski space, intrinsically you are putting C equal 1.
Yeah, and I don't think, I'll just say, to actually specify the geometry here, I mean, mathematically, it's specified by an incidence matrix that just tells me which n elements bound which n plus 1 elements. If I in terms of the spatial geometry and then in terms of the temporal geometry, it's just which ones are immediate successors of which ones. So all of this would just be done by incidence matrices and simple things that don't actually involve any distance parameter or anything like that in their specification. Okay, so first of all, thank you so much, dear Tim, for having accepted our invitation and for your talk. It was very interesting for me. There were so many questions that I had even zero time to ask my own question. I am sorry for Massimo. There is still one more raised hand, but he already asked the question and I think it's time to finish the talk. I would like to remind to the participants, to the listener, that the next talk will be on the 15th, next week on the 15th of September
on an infinite of worlds, cosmic inflation at the beginning of the universe with Willie Kinney from the University of Buffalo in the USA. So thank you again to all of you, and thank you, dear Tim, for your talk.